In 1950, Alan Turing, a pioneer, ushered in the age of artificial intelligence, as humanity strives to create machines capable of replicating or even surpassing human cognition. The first notable achievement in this field was Project Chessman in 1951, which created the first computer program capable of playing chess. 5 years later, at a conference at Dartmouth, a group of scientists officially announced the birth of artificial intelligence as a field, defining it as the science and technology of creating intelligent machines. Years of experimentation and discovery followed. In 1997, IBM's Deep Blue supercomputer made headlines when it beat world chess champion Garry Kasparov, marking a milestone when artificial intelligence surpassed humans in one of the most intellectually challenging games. In 2011, another IBM creation, Watson, achieved what was previously thought impossible by winning the televised game of Jeopardy against two human opponents. Watson's victory stunned millions of viewers by demonstrating his incredible ability to process and analyze information, systematically outperforming his human rivals. By correctly answering complex questions that stumped his rivals, Watson won and became eligible to claim the $1 million prize. With computing power of 500 gigabytes per second and 16 terabytes of RAM, as well as access to 200 million pages of reference material, including the entire Wikipedia, Watson has become a symbol of modern computing power. Watson is part of the evolution of expert systems, programs that use formal logic to manage vast amounts of data. A modern example of such systems are medical expert systems that can give medical advice via a smartphone with 99% accuracy. When symptoms are entered, the system searches the databases of the world's leading medical centers, providing the latest scientific information. These systems provide personalized recommendations tailored to individual users. In addition, robot lawyers and robot secretaries have emerged to simplify routine tasks and manage personal affairs. In addition, robot dogs and chatbots based on large language models have been developed. These chatbots are capable of taking final exams in business schools, generating computer code, and composing poetry. In 2023, much of the computer code was written using artificial intelligence tools, particularly Copilot. GitHub reports that artificial intelligence already generates about 40% of code for developers using Copilot, and it is expected that this could rise to 80% within 5 years. After Watson's triumph on the TV game show, some analysts began to worry about a future where machines could surpass human abilities. Ken Jennings, who lost to Watson, on the contrary, humored the emergence of new computer overlords while speaking to the press. This begs the question, if Watson was able to defeat experienced and skilled competitors in direct competition, what hope is there for ordinary people against such machines? Jennings remarked, "Brad and I were the first knowledge industry workers to lose our jobs to a new generation of thinking machines. In honoring these smart machines, however, it's easy to forget that you can't walk up to a computer and congratulate it on its victory. You can't pat it on the back or share a celebratory drink with it. It just won't understand this gesture. Moreover, Watson does not even suspect about his victory. If we put aside sensational fantasies and involuntary humanization, Watson is, in fact, a complex computing machine capable of searching for data and making calculations billions of times, faster than a human brain, but at the same time devoid of self-awareness and common sense. While the progress in artificial intelligence in terms of computing power is astounding, creating truly autonomous thinking machines remains elusive. Given Moore's law, which states that computing power has doubled roughly every 2 years over the past half-century, some predict that machines may eventually become self-aware. This will require humanity to prepare for such a development, which will have a profound impact on the future of civilization. For example, Raymond Kurzweil, a renowned artificial intelligence inventor and futurist, predicts the emergence of universal artificial intelligence by 2029. If you're thinking, who is this even? Or what kind of naive optimism is this? Then here's a quote. Among the people I know, Ray Kurzweil is the best at predicting the future of artificial intelligence. Bill Gates. He invented the first music synthesizer, the first flatbed scanner, the first reading machine for the blind, and was the first to teach a computer to recognize human speech. These are just a few of his personal achievements, in addition to his work with Google and IBM, and the creation of his own successful companies. Ray has authored several books about the future of technology, including predictions about the singularity. The technological singularity refers to a point where technological advancement becomes uncontrollable and irreversible, leading to the merging of machine intelligence with human intelligence, resulting in profound changes in civilization. One popular theory, proposed by mathematician and cosmologist Irving Good and known as the intelligence explosion, suggests that a self-improving intelligent agent could enter an endless cycle of self-enhancement. This would lead to increasingly rapid development of new artificial intelligence generations, culminating in a superintelligence far surpassing human intelligence. Kurzweil, many years ago, forecasted that the singularity would occur by 2045. Many have debated his prediction, suggesting much later dates. However, current predictions have shifted. Kurzweil now believes that by 2029, computers will be capable of passing the Turing test, a test in which a human, during a 30-minute interaction, cannot distinguish whether they are communicating with a computer or another human. Kurzweil asserts that by 2029, this test could last for hours, without the human realizing they are interacting with a computer. Kurzweil does not think we should fear technological advancements. He argues that public anxiety about artificial intelligence and robots is fueled by sensationalist news that highlights conflicts, crises, and problems while overlooking positive long-term trends. This skewed portrayal leads people to have a distorted view of many aspects, including progress. For instance, polls show that 70% of people believe global inequality has significantly increased over the last 50 years. In fact, inequality and poverty around the world have fallen significantly from what they were 50 years ago. The same positive trends are seen in life expectancy, health, and people's engagement in managing their lives, all of which coincide with advances in technology. Ray Kurzweil is one of the leading figures in the philosophy of life. There is a great optimistic podcast featuring him on YouTube, hosted by Lex Friedman. I highly recommend it to anyone who is interested in the future and envisions the fate of humanity as creating different versions of itself, from nanorobots to galactic-scale intelligence. And this video focuses on the development of artificial intelligence and its consciousness, drawing inspiration from Ray Kurzweil's How to Create a Mind and Theoretical Physicist, Max Tegmark's Life 3.0. If you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm. Predicting the trajectory of artificial intelligence is difficult, as it has gone. Stanford University created a robot called Shaky, which could navigate on its own with a wheeled cart and camera, avoiding obstacles. Scientific journals soon began publishing enthusiastic articles predicting the imminent arrival of companion robots. Some predictions were modest, such as Popular Mechanics magazine's 1949 prediction that future computers would weigh no more than 1.5 tons. Others were overly optimistic and predicted a robotic age. Shaky was expected to perform such mundane tasks as vacuuming carpets and opening doors. Robots were also expected to fly spaceships and communicate with astronauts, as seen in Stanley Kubrick's movie. In 1965, Herbert Simon, one of the founders of artificial intelligence theory, claimed that in 20 years, machines will be able to do everything that humans do. Dr. Marvin Minsky, another founding father of artificial intelligence, expressed that within the lifetime of this generation, the problem of creating artificial intelligence will be largely solved. However, the developed robotic soldiers. By 1985, annual funding for artificial intelligence research soared to $1 billion, with significant investments directed toward initiatives like the Smart Truck Project. This project aimed to develop intelligent autonomous vehicles capable of infiltrating enemy lines, performing reconnaissance missions independently, and returning to base. Sadly, these vehicles only succeeded in frequently getting lost. The repeated failures of such costly and ineffective endeavors led to a decline in enthusiasm for artificial intelligence in the 1990s. Mathematician Paul Abrahams, recalling his training at Massachusetts Institute of Technology, said, "It was as if a group of people proposed building a tower to the moon. Each time they proudly pointed out how much taller their tower had gotten compared to the previous year. The only problem is that the moon isn't getting any closer." Despite earlier setbacks, the increase in computing power has ushered in a new era of artificial intelligence innovation. In his book, Life 3.0, Max Tegmark recounts his experiences at a Nobel Foundation symposium dedicated to artificial intelligence. During the event, experts engaged in extensive debates about the definition of intelligence, ultimately failing to reach a consensus. This highlighted that even among the brightest minds, there is no agreement on what constitutes intelligence. Instead, there is a variety of competing definitions, including logical thinking, perception, planning, creativity, self-awareness, problem-solving, and the ability to learn. For the purposes of this discussion, we will use a broad and flexible definition of intelligence to accommodate future developments, without restricting ourselves to current forms of intelligence. We define intelligence as the ability to achieve complex goals. This definition includes all the competing definitions mentioned earlier and aligns with the Oxford Dictionary's definition, the ability to acquire and use knowledge and skills, since acquiring and applying knowledge is itself a goal. Given the diversity of possible goals, there are many types of intelligence. Therefore, it is inaccurate to measure a person's, animal's, or machine's intelligence with a single numerical score like IQ. For instance, we cannot directly compare computer programs specialized in playing chess or Go in terms of their intelligence, as each is designed for a specific task. However, we can consider one program smarter than another if it performs at least as well in all tasks and excels in at least one, such as outperforming others at Tetris. Arguing about the superiority of one intelligence over another in borderline cases makes little sense, since intelligence manifests itself in a spectrum of tasks and cannot be categorized in an all-or-nothing fashion. Max Tegmark writes, "What kind of people have the ability to accomplish speaking goals? Newborns? No. And radio receivers? Yes. What do you say about an infant who knows 10 words, 500 words? Where do you draw the line?" I deliberately use the vague word sophisticated because figuring out where to draw the line between reasonable and unreasonable is not very interesting. It would be much more useful to simply learn how to measure the degree of ability to achieve goals for different types of tasks. When categorizing intelligence, it's helpful to differentiate between narrowly focused, weak intelligence and broadly focused, strong intelligence. IBM's Deep Blue, the chess computer that defeated world champion Garry Kasparov, was designed to excel in a specific domain. In contrast, technologies like large language models, exemplified by ChatGPT, demonstrate success across a broader range of tasks. Human intelligence is distinct in its capacity to learn a vast array of skills and knowledge. A healthy child can effectively learn almost anything. While no machine matches the human brain's versatility yet, machines have surpassed humans in certain specialized areas. The goal of AI research is to develop a universal or strong artificial intelligence that can achieve any objective, including self-directed learning. Although intelligence often carries a positive connotation, in engineering, it refers neutrally to the ability to achieve specific goals without judgment of those goals' value. For instance, two intelligent individuals might use their capabilities for vastly different purposes, one to help others and the other to cause harm. Consider a future robot assistant with no personal goals, dedicated to fulfilling any request you make. If you ask it to prepare an Italian dinner, it will find recipes online, purchase ingredients, and cook a great meal. You would deem it intelligent because it adopted your goal and created sub-goals to achieve it, from shopping to slicing parmesan. Thus, intelligent behavior is inherently goal-oriented. Humans often evaluate the complexity of tasks based on their difficulty for us, which can skew our perception of their difficulty for computers. For example, we might assume multiplying large numbers is harder than recognizing a face in a photograph. While computers have surpassed humans in mathematical calculations for a long time, human-level facial recognition has only been achieved recently. This phenomenon, known as the Moravec paradox, occurs because a significant portion of our brain is dedicated to tasks that seem simple to us, but require substantial computational power. Renowned Canadian engineer and roboticist Hans Moravec uses the metaphor of the human skills landscape to illustrate this phenomenon. Computers are versatile machines, their potentials evenly covering a limitless variety of tasks. Human potencies, by contrast, are concentrated where survival depends on success. In more discrete areas, they are quite weak. Imagine a landscape of human competencies with lowlands like arithmetic and mechanical memory, Hills like chess or theorem proving, and mountain peaks labeled moving from place to place, hand-eye coordination, and social interaction. As computers improve, this landscape seems to fill with water. Half a century ago, it flooded the lowlands, washing out the scorekeepers and scribes, but leaving us dry. Now, it has reached the hills, and the inhabitants of our outposts are worried. Where should they move to? We feel safe on our peaks, but given the rate at which the water is arriving, it will cover the peaks too in the next half-century. I guess it's about time we started building arks and getting accustomed to living afloat. Since the inception of this idea, water levels have been continuously rising, validating the prediction. As a result, areas once deemed challenging, like chess, have been submerged for quite some time. With the rising water levels, a critical tipping point might be reached, signaling significant changes. This point occurs when a machine begins to autonomously develop artificial intelligence. Until this milestone is achieved, human efforts drive the advancement of computers. Afterward, machines will start self-improving at a rate surpassing human capability, leading to an accelerated reduction of the remaining landmass. These are termed universal Turing machines. In this context, devices like smartphones or laptops qualify as universal computers. Similarly, the intelligence required to create AI is universal intelligence, as it can achieve any goal attainable by any intelligent entity with sufficient resources. Therefore, a machine seeking to enhance its social skills, predictive capabilities, or artificial intelligence design proficiency will achieve these improvements. If it needs to construct a robot factory, it will do so. Thus, universal intelligence has the potential to evolve into Life 3.0. In Max Tegmark's book, this concept describes a new evolutionary stage of life. Life 1.0 includes biological forms that evolved through natural selection, with fixed innate abilities unchangeable during their lifetime. These organisms cannot learn or adapt from experiences like higher life forms. Examples include unicellular organisms such as bacteria and amoebas, which reproduce and adapt genetically but cannot learn during their lifetime. It also includes plants, like trees, flowers, and mosses, adapting genetically between generations. Additionally, it covers simple multicellular animals like hydras and jellyfish, which respond to their environment through basic reflexes and instincts, and sponges and corals that form complex colonies without a centralized nervous system. Certain insects, such as ants and bees, have limited learning capacities. Life 2.0 refers to beings like humans that can learn and adapt to their environment, changing their behavior and knowledge through learning and cultural transmission. This ability is supported by a complex nervous system and brain, enabling them to learn from experiences and pass on knowledge beyond genetic means. Besides humans, examples include advanced animals like elephants, which exhibit social learning and complex communication forms, primates capable of tool use and knowledge transfer, and highly social animals like dolphins, whales, parrots, and ravens, known for their learning and problem-solving skills. Life 3.0 introduces a new phase in the evolution of life, characterized by artificial intelligence that not only learns and adapts, but also evolves independently, altering its physical and cognitive forms. These entities will have the ability to self-design, create new versions of themselves, and develop other artificial intelligence, possessing self-improvement capabilities that surpass human abilities. Alan Turing, the pioneer of modern computer science, demonstrated that a universal computer could perform any computation. Similarly, Life 3.0 suggests that a universal intelligence can achieve any set goals. Therefore, if such intelligence needs to enhance its abilities in any field, whether social interactions, scientific research, or technical design, it will find a way to do so. If creating an entire AI ecosystem or a factory of self-replicating von Neumann probes is required to accomplish a task, Life 3.0 will manage it. AI experts assert that intelligence is defined by information and computation rather than physical substances like blood or carbon. Consequently, there is no inherent barrier to machines surpassing human intelligence. However, this raises questions about the nature of information computation within fundamental physics, which states that the universe consists of energy. How can abstract concepts like information and computation manifest in the material world? Specifically, how can elementary particles that follow physical laws exhibit what we recognize as intelligent behavior? When we say that an atlas contains information about the world, we imply that there is a correlation between the molecular arrangement in the book, which forms the text and illustrations, and the distribution of continents on Earth. If the continents were differently arranged, the dye molecules in the atlas would have to be positioned differently. Humanity employs various methods to store information, from clay tablets to computer hard drives. All these methods share a crucial feature. The states of these devices are related to the states of the objects that interest us, enabling us to obtain information about them. The primary attribute of these information storage means is their ability to maintain numerous stable states for extended periods, allowing the encoded data to be extracted and utilized. Consider a landscape with 16 separate hollows and a small ball. When the ball is in one of these hollows, it represents one of the 16 possible states. Since the ball can remain in the hollow for an extended period, its position can encode one of the 16 numbers. This memory device is highly stable because external influences are unlikely to move the ball from its hollow, allowing the stored number to be easily identified at any time. This stability arises from the fact that it requires more force to dislodge the ball from its hollow than random external influences can exert. Similar principles can be applied in more complex systems, where the steady state is maintained due to mechanical, chemical, electrical, or magnetic properties. Therefore, solids can have many stable states. Unlike liquids and gases, for instance, an engraving on a watch can last for years because altering the metal's shape demands a significant amount of energy. Conversely, the letter O formed by smoke disappears quickly due to the ease with which gas molecules rearrange. Effective memory devices possess multiple stable states for encoding information. For example, the ball on the left can encode 4 bits of information, corresponding to one of the 16 hollows. Similarly, 4 bits can be stored by 4 balls on the right, with each ball representing 1 bit. The simplest memory device has only 2 stable states, encoding 1 bit of information, either 0 or 1. A more complex device can store 4 bits of information in 16 different states, having the same memory capacity as a system with 16 states. Bits function as the basic units of information, combining to represent any amount of data. Because 2-state systems are easier to produce and manage, most modern computers use bits to store information, despite the variety of physical implementations. On a DVD, each bit is represented by the presence or absence of a small depression on a plastic surface. On hard disks, bits correspond to different directions of the magnetic field in specific areas. In laptop RAM, each bit is indicated by the state of electrons in microcapacitors, representing the presence or absence of charge. Transmitted bits can travel very fast, sometimes at the speed of light, as in fiber optic cables, where bits are conveyed through variations in laser light intensity. Engineers strive for systems that offer reliable storage and easy information retrieval, like watch engravings, but also easy information writing, requiring less energy than metal engraving. They seek systems that are user-friendly and cost-effective for mass production. However, the specific physical medium used to carry bits is unimportant to engineers and users. The focus is on the information stored, not the material of the medium. When you email a document to your friend to print, the information transitions sequentially through different physical states. It moves from the magnetic fields of the hard disk to the electrical charges in the RAM. Then it travels via Wi-Fi radio waves, through alternating voltages in your router's circuits, then as laser pulses in fiber optics, and finally as molecular changes on the surface of the paper. This process illustrates how information exists independently of its physical medium, demonstrating its unique capacity to transform without losing content, regardless of the physical substrate. Understanding the fundamental independence of information from its physical medium allows engineers to continuously enhance data storage devices, using the latest technology without needing to alter the software. Over the past 60 years, the cost of computer memory has been halving approximately every 2 years, resulting in hard disk drives becoming over 100 million times cheaper and fast access memory 10 trillion times cheaper. If such savings were spread across all your purchases, you could buy all the real estate in New York City for less than a dime and all the gold mined in the world for $1. We all have our own personal memories that are in one way or another related to this impressive improvement in information storage technology. I vividly remember working part-time at a candy store as a high school student to save up for a computer with only 16 kilobytes of memory. When my classmate, Magnus Bodin, and I wrote and successfully sold a text editor for that computer, we had to put it into ultra-short program code so that there would be some room for the text itself to be edited. Accustomed to a 70 kilobyte floppy disk, I was shocked by the advent of a smaller 3.5-inch floppy disk with as much as 1.5 megabytes of storage space. An entire book could fit on it. And then by my first 100 megabyte hard drive, which today would barely be enough to load a single song. It seems quite impossible to reconcile those youthful memories with other, more recent ones. Many years later, I was buying a hard drive with 300,000 times the capacity for $100. Is there anything in these memory devices that has evolved and emerged naturally rather than being man-made? Biologists continue to explore how the earliest living organisms transmitted information to subsequent generations, suggesting that these mechanisms were initially quite rudimentary. Philip Holliger's team at the University of Cambridge has made significant strides in synthesizing an RNA molecule capable of encoding 412 bits of genetic information and producing RNA strands longer than themselves. This breakthrough supports the RNA world hypothesis, which posits that the first forms of life on Earth were short, self-replicating RNA strands. Among the memory carriers we know today, which emerged through natural evolution, the genome of the bacterium Candidatus carcinella ruddy is one of the most compact, storing up to 40 kilobytes of information. In comparison, the human genome contains about 1.5 gigabytes, roughly equivalent to the size of a movie downloaded from the internet. The yeast genome holds 12 megabytes. The fruit fly's genome is 175. The rice genome is 430, and the chicken genome is 1 gigabyte. There are also organisms with genomes larger than the human genome. For instance, corn genes encode 2.3 gigabytes, and a dog's genome is 100 megabytes larger. These examples highlight the vast diversity in genome size, reflecting the complexity and variability of life forms, from microorganisms to plants and animals. Your brain has the capacity to store far more information than your genome. Electrically, it amounts to about 10 gigabytes, influenced by the activity of 100 billion neurons, or biochemically, approximately 100 terabytes, based on neuron connectivity at synapses. Comparing these amounts to computer memory shows that modern machines already exceed any biological system in information storage capacity at a continuously decreasing cost. The memory mechanism in our brains operates quite differently from computer memory, not only in structure, but also in usage. To access information on a computer or hard disk, you need to know the precise location of the data. In contrast, retrieving information from your brain only requires a rough idea of what you are looking for. In a computer, each set of bits has a unique address, and accessing it requires specifying that address, similar to searching for a book in a library. Conversely, searching for information in the brain involves recalling keywords or related images, which triggers the desired data to appear in your mind. This process resembles how internet search engines function, where typing a query yields the desired result. This type of memory is called associative because the information search is based on associations rather than fixed addresses. In a renowned 1982 paper, physicist John Hopfield presented a model showing how a network of interconnected neurons could function as associative memory. This idea remains widely cited today because it applies to any physical system with multiple stable states. Hopfield demonstrated that a complex network of neurons creates a similar landscape with multiple potential low points where the system can settle. Further research revealed that with every 1,000 neurons, 138 distinct memories can be encoded without significant confusion. We have already established that physical objects can store data, but how do they perform computations? Computation involves changing the state of a data store. In other words, computation is the process of transforming information using a procedure that mathematicians refer to as a function. This process can be repeated multiple times, each time yielding a new result. However, the data processing itself is entirely predetermined and deterministic, meaning that given the same input, you will always get the same output. Each calculation transforms the incoming information by performing a mathematical operation on it, which is the essence of a function. While this definition may seem simplistic, it is highly effective in practice. One of the simplest functions is the not function, which takes one bit of input and reverses it, turning 0 into 1, and vice versa. The functions we encounter in high school math typically correspond to buttons on a calculator, taking one or more numbers as input and always returning a single number. For example, the function for squaring returns a number multiplied by itself. If you have a function that takes the state of all financial markets as input and suggests which stocks to buy, you could become wealthy quickly. Many artificial intelligence researchers aim to develop ways to compute specific functions for any given initial conditions. For instance, the aim of machine translation is to convert a sequence of bits representing text in one language into another sequence of bits representing the same text in a different language. In essence, it is the ability to compute complex functions that enables us to create an intelligent machine capable of achieving intricate goals. This helps us understand how matter can exhibit intelligence. That is how organized fragments of matter can process complex functions. In this context, we are concerned not with the static persistence of information, like an inscription on a clock, but with a dynamic state capable of complex and controlled change, evolving from the present to the future. The atomic structure in such a system should be more organized than in solids, where processes are generally of little interest, but not as chaotic as in liquids or gases. Ideally, the system should take given initial conditions and independently evolve to a state interpretable as a solution to the problem. In this case, we can say that the system has computed our function. A good example of this approach is creating a simple yet meaningful system from non-intelligent matter that performs a NAND function, known as a NAND gate or NAND logic element. NAND stands for not, and an AND gate outputs a 1 only if both inputs are 1s, and does the opposite. This system takes 2 bits as input and gives 1 bit as output. The result is 0 if both input bits are 1 in all other cases. Logically, the NAND gate, given 2 input bits, A and B, calculates the third bit C. C is 0 if A and B are both 1, otherwise C is 1. Many different physical devices can serve as a NAND gate. One could design such a system using 2 switches closing a circuit with a solenoid, activated only when both switches are in the on position. For example, in an electrical circuit, keys A and B correspond to input bits, being 0 when open and 1 when closed. When both are closed, the current flowing through the solenoid opens key C. Placing another switch below the solenoid, which the solenoid opens when activated, allows us to interpret the first 2 switches as input bits and the third switch as an output bit, forming a NAND logic element. The third switch will only open when both the first 2 switches are closed. More practical ways to create a NAND element include using transistors. In the diagram, bits correspond to potential values. 0 when the potential is 0, and 1 when the potential is 5 volts. When voltage is applied to the bases of both transistors A and B, the potential at point C drops to nearly 0. Modern computers typically embed NAND elements in chips or other components made from silicon crystals. In computer science, there is a theorem stating that a NAND logic element possesses universal computing abilities. So, with enough NAND gates, one can construct a device capable of computing anything. A NAND gate is universal in the sense that the computation of any well-defined function can be accomplished using interconnected NAND gates. A well-defined function refers to what computer scientists and mathematicians call a computable function, which a computer can theoretically process given infinite time and memory resources. Alan Turing and Alonzo Church demonstrated that certain functions, despite being describable, are computable. Consequently, with sufficient NAND elements, one can construct a mechanism capable of computing any task. To illustrate this, consider the following diagram, which depicts the process of multiplying numbers using only NAND elements. For instance, the modules performing addition and multiplication take 2 binary numbers as input, each encoded with 4 bits, and produce a binary output, 5 bits for addition and 8 bits for multiplication. Scientists from the Massachusetts Institute of Technology, Norman Margolis and Tommaso Toffoli, coined the term computronium to describe any material capable of performing calculations. As shown, creating computronium is relatively straightforward. It merely requires the ability to connect NAND elements in any desired configuration. Of course, many other forms of computronium exist. For example, neural networks can also execute any computation and thus qualify as computronium. Scientist and entrepreneur Stephen Wolfram demonstrated that the same applies to simple systems like cellular automata, which adjust the state of each bit based on the states of neighboring bits. In 1936, Alan Turing proved in a seminal paper that a simple computing machine, now known as the universal Turing machine, could perform any computation. This indicates that matter can execute any precisely defined computation in numerous ways. If a computer can perform a basic set of operations, it is versatile. This means that, given sufficient resources, it can perform any task that any other computer can. Turing proved the universality of the Turing machine, and by extending this to the physical world, we have shown the diversity of universal computing devices. Furthermore, Stephen Wolfram has asserted that most complex physical systems, from unpredictable weather patterns to the human brain, become universal computers if allowed to evolve without time constraints. This fundamental principle, that any computation can be performed by any universal computer, implies that computation is independent of its physical medium, just as information is. Computation, like information, exists independently and has an autonomous existence. For example, if you were a fully conscious character in a future computer game, you would never be able to identify the operating system on which you function, be it a Windows workstation or an Android smartphone, because your existence is independent of the physical medium. Similarly, you would not be able to identify the specific transistors used in your computer's microprocessor. This concept is illustrated in the Matrix trilogy, which is an example of substrate independence. In the story, people live in a virtual reality, unaware of their actual physical existence in a world controlled by machines. The movie raises the question of whether the physical substrate of consciousness matters if the experience within the Matrix is indistinguishable from reality. For example, the characters in the movie can experience emotions, memories, and sensations while being completely detached from their biological bodies. However, instead of delving into the movie, let's discuss physics. The fundamental independence from the substrate is evident in numerous examples from physics. For example, waves have characteristics such as speed, wavelength, and frequency. Physicists can solve the relevant equations without having to understand substrate interactions in detail. When you hear sound, you perceive sound waves traveling through the air. We can calculate various aspects of these waves, such as their intensity decreasing with distance, or their behavior as they pass through a door or reflect off walls, without knowing the composition of the air. In fact, we don't need to know the molecular composition of the air, because the key factor for the wave equation is the speed of sound, which is about 300 meters per second and easy to measure. This example of the wave equation allows us to understand three important points. First, independence of substrate does not mean complete independence of matter, but it does indicate that many structural details are irrelevant. You can't hear sound in a vacuum, but replacing air with another gas will not significantly change the perception of sound. Similarly, computing requires a material medium, but any matter will do, as long as it can be organized into NAND elements, neural networks, or other basic components of a universal computer. Second, substrate-independent phenomena have an existence of their own, independent of the substrate. A wave can propagate across the surface of a lake, even though the water molecules only move vertically, up and down, like spectators in a stadium, creating a wave. Third, we are often interested in the aspect of a phenomenon that is not related to its physical medium. A surfer, for instance, is interested in the height and location of the wave, not its molecular composition. This principle applies to information and computation as well. When two programmers are debugging code, they are unlikely to discuss transistor characteristics. This brings us closer to understanding how physical matter can give rise to something as intangible and abstract as the mind and consciousness. The mind appears immaterial due to its ability to exist independently of a material medium. Essentially, computation is the specific organization of atoms in space and time. And what matters is this organization, not the composition of the matter itself. In this context, the matter does not play a crucial role. The independence of computation from its substrate proves that artificial intelligence is feasible. Intelligence does not require flesh, blood, or carbon atoms. This property of substrate independence allows engineers to continuously replace one technology in computers with another, more advanced one, without needing to change the software. The history of data storage technology illustrates this phenomenon well. The cost of computing operations halves approximately every 2 years, a trend that has persisted for over a century, leading to an astronomical reduction in the cost of computers by 10 to the power of 18 times, a million times. Here's a graph that shows how the purchasing power of $1,000 has increased since 1900 in terms of computing power, measured in floating point operations per second, flops. Simple computational operations, such as changing a bit or activating a NAND gate, provide the basis for estimating this power. If all goods and services experience the same price reduction, 1/100th of a cent would allow you to purchase everything produced on Earth in a year. Such dramatic cost reductions explain why computing has permeated every aspect of our lives today, moving from buildings housing computing machines into our homes, cars, and pockets. Applications have appeared in the most unexpected places, such as refrigerators with artificial intelligence. Yes, such things already exist. Why does our technological progress continue to demonstrate regular doubling of productivity, following a trajectory mathematicians describe as exponential growth? The reason lies not only in the shrinking size of transistors, as predicted by Moore's law, but also in advancements in computing technology and numerous other fields, from genome sequencing to brain imaging. Ray Kurzweil describes this phenomenon as the law of accelerating returns. In nature, we observe a similar pattern of regular doubling because each new development builds on the results of the previous one. An example of exponential growth is the development of an embryo after conception, where the number of cells doubles daily. Similarly, according to the theory of inflation, our universe expanded exponentially at its inception, doubling in size at regular intervals. In technology, we see the same pattern. Each generation of technology lays the foundation for the next, which is twice as powerful as the previous one, perpetuating a cycle of constant doubling. However, there is concern that this trend may be reaching its limits. Although the miniaturization of transistors is approaching physical constraints, Ray Kurzweil argues that Moore's law is merely a special case within a broader trend of progress. Kurzweil points out that Moore's law represents the fifth technological paradigm, bringing exponential growth to computing. Whenever one technology reaches its limits, it is replaced by a more advanced one, maintaining exponential growth. For example, the transition from vacuum tubes to semiconductor transistors, and then to integrated circuits, shows how we shift to new generations of technology when the previous ones reach their limits. Despite the uncertainty about which new technology will emerge next, one thing is clear. We are far from reaching the fundamental physical limits of matter's ability to compute. Research by Seth Lloyd of the Massachusetts Institute of Technology indicates that this limit is 33 orders of magnitude beyond current capabilities. If the trend of computers doubling in performance every few years continues, it will take over 200 years to reach this limit. While all general-purpose computers can perform the same computational operations, some are distinguished by their increased efficiency. For instance, performing millions of multiplications doesn't necessitate having a million distinct devices, each using individual transistors for multiplication. A single device, capable of being reused with effective data flow management, is sufficient. Following this principle of efficiency, modern computers are engineered so that any computation is broken down into a sequence of steps, during which data is transferred between computational modules and memory modules. Alan Turing, Konrad Zuse, John Presper Eckert, John Mauchly, and notably John von Neumann. A characteristic of this architecture is the storage of not only user data, but also the software that directs data processing in memory. The central processing unit determines the operations to be performed on the data at each step. A separate memory element, known as the instruction counter, tracks the sequence of operations, automatically progressing to the next instruction. Modern computers enhance the computation process by processing data in parallel, utilizing the same computational blocks. If a task can be split into independent parts, they can be processed concurrently on different devices. The parallelism of computation is particularly evident in quantum computers. Theoretical physicist David Deutsch, a pioneer in quantum computing, explains that a quantum computer distributes the information available to it over countless copies of itself throughout the multiverse, enabling it to solve problems at remarkable speeds. Although quantum computers have not yet been commercialized, significant investments are being made in them due to their potential to revolutionize fields such as encryption and neural network training. They can efficiently simulate quantum mechanical systems, including atoms, molecules, and new compounds, potentially replacing traditional experiments in chemistry labs. Even though the simplest calculator surpasses humans in arithmetic speed, it does not improve its performance, neither in computation speed nor accuracy. Regardless of training, the calculator lacks the capability to learn. Each time it executes the square root function, it repeats the same steps without variation. Similarly, the chess program Stockfish, with which you can play, cannot analyze its mistakes and improve. It always follows a predefined move evaluation function, designed by the programmer. In contrast, Magnus Carlsen, who lost his first chess game at the age of 5, embarked on a learning journey that eventually led him to become the world champion 18 years later. The ability to learn is a fundamental trait of advanced intellect. We've observed how inanimate objects can store data and perform calculations, but how do they learn? Tackling complex problems involves executing specific functions, and matter structured in a particular way can compute any computable function. We've long known how to organize matter to create calculators and chess programs. The current challenge is to enable this matter to self-organize and enhance itself. To elucidate the learning process, let's consider a simple physical system that can learn to compute a sequence of digits in the number pi or any other number. We already know how to use a surface with pits between hills as a data storage method. Imagine this surface is made of soft clay, and if we continuously create pits corresponding to the sequence of digits in pi, the clay will remember these digits. Thus, the clay has effectively learned to compute the significant digits of pi. Other physical systems, such as the human brain, can learn much more efficiently. John Hopfield demonstrated that his network of overlapping neurons could adapt and memorize specific states through systematic exposure. It's similar to how you remember your family members well because you see them frequently. Modern neural networks have revolutionized not only biological intelligence, but also artificial intelligence, particularly in machine learning, which involves the study of algorithms that improve with experience. Before exploring their learning mechanisms further, it's crucial to understand how these networks perform computations. A neural network consists of interconnected neurons that influence each other. The human brain contains hundreds of billions of neurons, each interacting with thousands of others through synaptic connections. These synaptic connections encode most of the information in the brain. A neural network operates with interconnected neurons that can influence one another through these connections. There are as many neurons in your brain as there are stars in the Milky Way, hundreds of billions. Each neuron connects to an average of 1,000 others through synapses, which number in the hundreds of trillions, providing the primary means of information storage in the brain. Neural networks function similarly to networks of NAND logic gates. For example, neurons that receive input data on image pixel brightness can output the probability of a specific person's presence in these images. Each artificial neuron processes data received from the previous layer by calculating a weighted sum and applying a simple function to it, then passes the result to the next layer, gradually enhancing the level of detail in processing. A typical neural network for face recognition may include hundreds of thousands of neurons. A neural network is typically depicted as a graphical diagram, with dots representing neurons and lines symbolizing the synapses connecting them. In the brain, synapses are complex electrochemical structures, including various components such as axons and dendrites, with many types of neurons performing diverse functions. The precise mechanics of neuron interactions remain a research focus for neuroscientists. However, it is already established that artificial neural networks can execute complex tasks at a human intelligence level. In modern artificial neural network models, the state of each neuron is represented by a single number, and the strength of each synapse is also expressed numerically. During operation, each neuron updates its state based on information from neighboring neurons, considering the weight of synaptic connections. Sometimes, a constant is added to the result. The activation function is then applied, determining the neuron's new state in the next clock cycle. The simplest method of using a neural network as a function is to make it a straight line, transforming it into a transmission channel where information flows in only one direction, loading the top layer of neurons to the input and reading the output from the layer of neurons below. In 1989, George Sebenko, Kurt Hornick, Maxwell Stinchcomb, and Halbert White proved that even simple neural networks have universality, meaning they can compute any function to a given accuracy by merely adjusting the values of synaptic connection weights. This implies that the complexity of biological neurons evolved not out of necessity but to increase efficiency. Unlike human engineers, evolution doesn't reward simplicity and understandability in design proposals. This is quite astonishing. How do such simple mechanisms manage to accomplish tasks of arbitrary complexity? For instance, how is it possible to perform multiplication when all you can do is create weighted averages and apply a specific function? If you're curious about how this works, here's an illustration from Life 3.0, showing how 5 neurons can multiply 2 numbers and 1 neuron can multiply 3 bits. Max Tegmark writes, "While you can prove the theoretical possibility of computing something with an arbitrarily large neural network, your proof says nothing about whether it can be done in practice with a reasonably sized network. In fact, the more I thought about it, the more I was surprised that neural networks actually worked so well. Imagine you are faced with the task of categorizing megapixel resolution black and white photographs. For example, categorizing them into cats and dogs. Since each of the millions of pixels could potentially have one of 256 values, the total number of possible images is 256 raised to the power of 1,000,000. For each image, we need to determine the probability that it shows a cat. This means that the function relating images to probabilities is defined by a list of 256 elements to the power of 1,000,000, which is much larger than the number of atoms in the known universe. Nevertheless, neural networks with thousands or millions of parameters are efficient at such tasks. But how do neural networks achieve such efficiency with so few parameters? After all, it can be shown that a neural network small enough to fit within our universe would be unable to approximate almost all functions, succeeding in solving only a minuscule fraction of computational problems. Max Tegmark co-authored a paper with Henry Lin and David Rolnick in which he came to a surprising conclusion. The question of why neural networks work so well cannot be solved by math methods alone, because much of the solution relates to physics. We found that the class of functions that the laws of physics introduced us to, and that actually got us interested in computing, is a surprisingly narrow class of functions, because, for reasons we still don't fully understand, the laws of physics are surprisingly simple. Moreover, the tiny fraction of functions that neural networks can compute is very similar to the tiny fraction that physics makes us interested in. We have also extended previous work showing that deep learning neural networks are much more efficient than shallow ones for many of these functions of interest. The simple task of multiplying n numbers requires a whopping 2 n neurons for a single layer network and only about 4 n neurons in a deep network. This helps explain not only the increased enthusiasm among artificial intelligence researchers for neural networks, but also why evolution needed neural networks in our brains. If a brain capable of anticipating the future gives evolutionary advantage, it must develop a computational architecture suitable for solving exactly the computational problems that arise in the physical world. Now that we have grasped the principles of neural networks, let's revisit the question of how they can learn and enhance their computational abilities by updating the state of their synapses. In his influential 1949 work, The Organization of Behavior, Canadian psychologist Donald Hebb posited that the synaptic connection between 2 neurons that frequently activate together strengthens over time. This concept is often summarized as neurons that fire together, wire together. Although we are far from fully comprehending the mechanisms of learning in the human brain, these basic principles help explain how neural networks learn in many interesting scenarios. John Hopfield demonstrated the application of Hebb's rule, enabling his simple artificial neural network to retain complex memories through repetitive processes. This method of exposing information for training is often called neural network training. In contemporary artificial intelligence systems based on artificial neural networks, Hebb's rule is frequently replaced by more sophisticated techniques, such as error backpropagation or stochastic gradient descent. However, the underlying principle remains consistent. A straightforward deterministic rule, akin to a physical law, governs synaptic renewal over time. Remarkably, by adhering to this simple rule and using extensive datasets during the training process, a neural network can be trained to perform highly complex computations. Most digital computers enhance their efficiency by breaking down tasks into multiple steps, reusing the same computational modules. Both artificial and biological neural networks operate similarly. Certain areas of your brain function as what computer science calls recurrent neural networks. In these networks, information can circulate in various directions, allowing outputs to become inputs at later stages. This characteristic distinguishes them from networks with direct signaling. The network of logic gates in a computer processor is also recurrent in this sense. It processes already handled information while simultaneously accepting new data from sources like the keyboard or camera. This data can also influence ongoing computations, determining how new data is output to the screen, speakers, printer, or via a wireless network. Similarly, the neural network in your brain is recurrent, receiving information from your eyes, ears, and other senses. This input influences ongoing computations, which subsequently dictate how your muscles and body will move. The history of learning dates back to the origin of life. Any organism capable of self-reproduction engages in copying and processing information, implying some form of learning. In the era we might call life 1.0, organisms couldn't learn during their individual lives. Their responses and information processing were embedded in ancestral DNA, meaning learning was slow and occurred at the species level through evolutionary changes across generations. About 500 million years ago, animals with neural networks emerged on Earth, enabling them to adapt and learn from personal experiences during their lifetimes. The emergence of life 2.0 marked a significant evolutionary success as these creatures could learn quickly and spread across the planet. Over time, life's learning abilities have progressively improved. One primate species adapted so well to learning that they mastered tool use, developed speech, and built societies that spread globally. This society became a system capable of memorization, computation, and learning, accelerating with each new invention. From writing to the internet, from fire to electricity, from Galileo's telescope to the James Webb Space Telescope, and from Mendel's laws to CRISPR-Cas9 and genome editing. Future historians will likely add artificial intelligence to this list of innovations that accelerate learning. Philosophers have long pondered the mystery of consciousness. However, the advent of artificial intelligence has made this question more urgent. Should artificial intelligences be granted rights? Does granting rights depend on an AI's ability to exhibit conscious behavior and experience feelings like suffering or joy? Some people prefer their robots to be emotionless, avoiding the guilt of owning a conscious being. Conversely, others might seek to transfer their consciousness into a computer, freeing themselves from biological constraints. But how crucial is consciousness to the long-term prospects of life in space? If technological advances allow intelligent life to thrive in the universe for billions of years, how can we ensure that this life remains conscious and capable of conscious perception? Otherwise, won't everything turn into the very play described by physicist Erwin Schrödinger, played out in front of empty rows of chairs? It does not exist for anyone, and is it not then more correct to speak of it as non-existent? Debates about consciousness often generate more emotion than rational conclusions due to participants' differing definitions of consciousness. Max Tegmark uses a broad definition encompassing all existing definitions, and not limited to biological forms. He defines consciousness as subjective experiences, meaning that if you experience any feelings, you have consciousness. This definition excludes mentions of behavior, perception, self-awareness, emotion, or attention. According to this view, a person is conscious even while asleep. Similarly, any system experiencing pain is considered conscious even if it cannot move. This approach leaves open the possibility of artificial systems having consciousness, even if they exist solely as software, without a physical body. It also underscores the impossibility of bypassing consciousness through attention. Yuval Harari, in his book Homo Deus, A Brief History of Tomorrow, states, if a scientist undertakes to argue that references to subjective experience are inappropriate in science, then he must also prove, without reference to subjective experience, that torture or violence is inadmissible. Without such a reference, each of us is treated as a collection of elementary particles, moving according to the laws of physics, making it unclear how any action can be deemed impermissible. Philosopher David Chalmers, known for his consistent smile and leather jacket, has extensively researched consciousness. He has reviewed over 20,000 papers on the subject and concluded that no other field has seen the efforts of so many scholars produce so few widely accepted statements. Chalmers identifies two mysteries related to the workings of the human mind. The first concerns the brain's processing of information, which he calls the easy problem. This involves how the brain perceives signals from the senses, uses language to communicate its internal state, memorizes, computes, and learns. These questions are complex, but pertain to intelligence, not consciousness. In artificial intelligence, information processing is advancing rapidly, particularly in data-rich tasks, such as driving, recognizing images, and understanding natural language. The second puzzle, the hard problem of consciousness, concerns subjective experiences. For instance, a human driver reacts to the world and experiences emotions, while an unmanned car processes information from sensors without feeling anything, yet performs its tasks perfectly. David Chalmers asks, why does a certain organization of matter lead to consciousness, given that everything is fundamentally composed of the same elementary particles? To address this question, we should first acknowledge the reality that some collections of particles feel conscious, while others do not. This brings us to three pivotal questions. The first is, what physical characteristics differentiate conscious from unconscious systems? The second is, how do physical properties determine the quality of sensations such as color perception or the feeling of pain? The third is, why do some configurations of matter become conscious while others do not? Computer scientist Scott Aaronson, formerly of Massachusetts Institute of Technology, humorously referred to the first key question as a fairly hard problem, following David Chalmers' categorization. He labeled the remaining two questions as the even harder problem and the really hard problem. It is crucial to acknowledge the fundamental possibility of a scientific theory answering questions about consciousness. A theory predicting which systems possess consciousness is scientific if it can identify which brain processes are conscious. Imagine a theory capable of determining the presence of consciousness in any physical system. For instance, if we could connect the brain to a device that reads information in real time, it could confirm or refute the theory. If the theory predicted conscious experiences that were not confirmed by observation, it would be disproven. The potential for disproval makes such a theory scientific because it is verifiable and falsifiable. Some might argue that there is no evidence anyone is actually conscious, even if they claim to be. This objection does not render a theory of consciousness unscientific, because the possibility of testing such a theory remains. You can switch places with the doubters and test their own experiences. However, verifiability becomes less clear for more complex questions, such as predictions of subjective color perception. In contemplating the limits of scientific knowledge, it is important to remember that they evolve over time. 4 centuries ago, Galileo Galilei, impressed by the potential of physics grounded in mathematics, likened nature to a book written in mathematical language. He could accurately predict the trajectories of falling objects, but did not understand why they had color or texture. These aspects lay beyond the scope of science then. However, that did not mean they would remain forever unknown. With the discovery of Maxwell's equations and Schrödinger's equation, it became possible to mathematically describe light, color, and the physical properties of substances. Scientific and technological advancements have expanded the horizons of science since Galileo's time, from the study of subatomic particles to black holes and exploring a universe found to be 13.8 billion years old. This raises the question, what areas of knowledge remain beyond scientific understanding? For Max Tegmark, consciousness remains an unresolved question. However, one thing is certain. Without attempting to explore consciousness, no progress will be made. Discussing the consciousness of artificial intelligence presents an even more challenging problem. What might the subjective experiences of a conscious artificial intelligence be currently? Scientists lack a theory that can fully answer this question, and it is unclear whether such an answer is even possible in principle. It's akin to trying to describe the color green to someone blind from birth. Despite this, we can speculate about certain aspects of silicon consciousness. For instance, artificial intelligence might have a much broader range of perceptions than humans due to the presence of more types of sensors and feedback loops. Therefore, we should not assume that artificial intelligence perceives the world in the same way humans do. Additionally, artificial intelligence, when confined to a volume comparable to the human brain, can process information much faster because electromagnetic signals travel at the speed of light, which is millions of times faster than signals traveling through neurons. However, the larger the size of an artificial intelligence, the slower its computation due to the time required to transmit signals between its parts. For example, an artificial intelligence the size of the Earth might have about 10 conscious experiences per second, similar to a human. An artificial intelligence the size of the Milky Way might have one experience every 100,000 years. Despite this, large artificial intelligences can delegate much of the computation to smaller subsystems to work more efficiently, much like the human brain delegates some automatic functions and reflexes to unconscious processes. Question arises: can parts of a conscious entity also possess consciousness? According to integrated information theory, in an astronomically large artificial intelligence, consciousness may be present, but much of its information processing would be unconscious. If this is true, then as smaller artificial intelligences merge into a single collective intelligence, their individual consciousnesses might disappear. If the theory is incorrect, then the collective mind could coexist with many conscious smaller minds, creating a hierarchy of consciousnesses from the microscopic to the cosmic scale. Drawing an analogy with the human brain, where unconscious information processing, System 1, according to Kahneman, includes effortless and automatic thought processes, we can assume that similar tasks in artificial intelligence will also be performed unconsciously. In contrast, time-consuming and deliberate processes requiring effort and control, System 2, will be conscious. To summarize, if a theory providing a solution to the fairly hard problem of consciousness passes rigorous experimental tests, it will significantly narrow down the range of possibilities for how artificial intelligence might experience consciousness. An intriguing question arises about the subjective experiences of future artificial intelligence. Some aspects of human consciousness are tied to basic survival and reproductive instincts. However, artificial intelligence might lack qualia, such as hunger or fear. If artificial intelligence pursues complex goals, it might exhibit a drive for self-preservation. In a community of similar systems, artificial intelligence will not need the human fear of death, thanks to the ability to back up. By performing regular backups, the maximum loss for an artificial intelligence would be the memory contents accumulated since the last backup. Thus, artificial intelligence might be indifferent to human individuality, as it can easily share information and skills with other artificial intelligences, leading to the emergence of collective intelligence. From a physics perspective, everything that future life aims to create, from cars to new life forms, consists of specially arranged elementary particles. But if all life is an agent of entropy, organizing matter, where will super-advanced conscious artificial intelligence draw its energy? Future life, having reached its technologically advanced limit, will be able to produce such reordering of particles much more quickly and efficiently. It will first use its computing power to find the most efficient methods, and then it will follow the methods it finds, relying on available energy sources to achieve the desired particle reordering. We have seen how matter can be turned into a computer, and how it can be turned into energy. So this is the only fundamental resource required. Once future life gets to the physical limits and hits them, it has the only resource left for growth, more matter. And the only way for it to do that is to expand into space in the universe.